You are welcome to ST Pass International College. Kindly subscribe to this channel, like the video, and share to your friends in other schools. Um, Once again, we are going to start with a new topic, and I will urge you to follow or watch the video to the end of this lesson. In today's presentation, we are going to discuss everything on periodic chemistry. This is an interesting topic, and we are going to talk about this topic into details. Everything related to periodic chemistry we are going to discuss today. So don't miss this video, watch it to the end. But I want to talk about periodic chemistry. There are certain things you need to take notice of, and there are some scientists who have contributed to the arrangement of elements on the periodic table. So periodic chemistry, we are going to look at a lot of variations on the periodic table, and the trends on the periodic table, the variations as a result of some scientists who have contributed in trying to group these elements. So first of all, before we start, I would like to give a short history about some of these scientists and their contributions to this study. So the first person I would like to talk about is called Dobrinus. Johannes Dobrinus. He brought a concept called Dobrinus trians. This scientist, in the year 1817, started bringing some concepts on Dobrinus, or how these elements were arranged. We can say that Dobrinus is, I would say, Dobrinus is a renowned scientist, and due to his contribution, he was trying to group some elements during his time. But during his time, few elements were discovered by then. About 30 elements were discovered during his time. But this man tried to group some of the elements in a group of three. So when he said trians, trians simply means a group of three. So what Dobrinus did was, he picked an element like lithium, an element like sodium, and an element like potassium. So if you look at these three elements, he tried to group these elements in a group of three. Then we could also pick elements like chlorine, bromine, iodine. So when you pick your periodic table, you can see the trends there. So let me quickly go visit the table. So let's look at the arrangement. Let's consider the second group element first. You also look at these elements: calcium, strontium, and then barium. And the third element he studied was chlorine, bromine, and then he studied something about iodine. So these are the elements he studied. Now we want to find out the theory behind his trians. Dobrinus tried to group these elements in a group of three. Now this is what his findings. He said that the atomic numbers of the first element, which is lithium, so we are going to consider the atomic number of lithium, which is approximately, it's approximately 7, plus this is approximately 39. He said when you add these two and you divide by 2, the answer should give you the atomic mass or the mass number of the middle element. So with this example, it means that when you're able to add this, you are going to get 46. And so when you divide this 46 into 2, that gives us 23. What it implies is that the 23 becomes the mass number of the middle element. And that was his principle or his proposal, which is called Dobrinus trians. He did the same thing to calcium. So when you also want to find out of calcium, you add the mass number of calcium plus that of barium. Then you find the midpoint, or you divide it by 2. That will give you the middle mass number of strontium. The same thing applies to chlorine. We add the mass number of chlorine to that of iodine, and you find the midpoint, or you divide by 2. It gives you the mass number of bromine. So that was his concept. And because he couldn't group all these elements, he couldn't follow the trend, couldn't follow with all the other elements. So he had what we call limitations. The limitation he had, one of them is he couldn't group all the elements that were existing by his time, but he could only group 9 elements. So WNS had a limitation and paved the way for another great scientist who took over from him. Now, the next scientist who took over from WNS also did a marvelous work, which we would like to talk about and recommend him for that. John Newland, an English chemist. This man also brought a proposal. Newland, which we call the Newland law of octave. Now, when you're a music student, anytime you hear the word octave, it gives you a very sound meaning of sounds. So this chemist, English chemist, was using sounds to group the elements. Now, this is how he groups his elements. It depends on where you are watching him from, the country you are watching him from, and the manner or the kind of music you normally do in your countries. But in a part of our work where we are doing this presentation, we are familiar with these musical terms like do, re, mi, fa, sol, la, ti, do. So that is a musical term. That was a musical term this scientist was using to group his elements. So we call that principle Newland law of octave. Now, what is Newland trying to do? Let's look at how he arranged his elements. So he started arranging the elements in this manner. Now, this is how we arrange his elements. So, if you want to start with the sounds, do, re, mi, fa, sol, la, ti, do, you will realize that as you are moving, do, re, mi, fa, sol, la, ti, you come back to do on the octave, that is the eighth. Let's look at this. 1, 2, 3, 4, 5, 6, 7. On the octave, on the eighth element, you come back to this element. And that is how we arrange these elements. And he was arranging these elements based on the principle. You realize that these elements belong to the same group, and these elements have similar chemical properties. When you pick these elements, they are also in the same group, exhibiting the same chemical properties. When you pick these elements, they are also in the same group, exhibiting the same chemical properties. Now, from his grouping, you could realize that there were some elements exempted. So this had a limitation. Now, after first 20 elements, if you want to continue from scandium, titanium, vanadium, chromium, you realize that you have a problem. Now, this aluminum is not under this scandium is not under this aluminum when we are grouping the element, because they don't have the same chemical properties. This silicon is not under titanium. They are not having the same chemical property. So this scientist also had what we call limitation. So there is the need to pave a way for another great scientist to also continue from where he ended. So we had another great famous chemist, which we are proud of. He's a Russian chemist born in the year 8 February 1834 and died on, I think, 22nd February 1907. This famous scientist in the year 1869 brought a very nice concept which chemists have accepted all over the world. And this scientist is named Dmitry Mendeleev. Dmitry Mendeleev. This great scientist was able to group elements in columns and in rows. Or he was able to group elements in groups and in periods. Now, I want to combine the work of this great chemist to that of one famous chemist known as Henry Moseley. Now, these two scientists or chemists brought about what we call the modern periodic chemistry or periodic table. This man started naming or grouping elements in groups and in periods. So we call him the father of periodic table or periodic chemistry. He's the father of the periodic table. He was able to group these elements into groups and in period. Now, with this little history, Henry assisted him. This man was only able to group the elements in 8 groups and then some few periods. But Henry assisted him, built upon his principle, and now we have managed to group these elements into 18 groups and 7 periods. And that is what basically we are going to study about. We are going to look at how he grouped these elements and what they are meant for. So let's look at how this man grouped these elements. So starting from a place, let's have a skeletal view of this, and then we'll come to the main elements. So this is how he grouped his elements. They divided them into blocks. So on the periodic table, we have this called the S block. They did a very wonderful work. Then we have this called the D block, or what you call the transition metals. Transition metals. Then we have the P block. Then we have the F block. Now the question is, why name F, S, P, and all that? Now, these elements on the periodic table, the names of these blocks were derived from the orbitals. So we are going to link this to the orbital for us to get a clearer view and understanding of the periodic table. Now this S block is what we refer to as the S orbital. Now when you say an orbital is the volume of space in which there is a higher probability or possibility of finding an electron. So there are electrons, and the elements in there have electrons. So there's a higher possibility or probability of finding an electron on this periodic table. So the S block, which we normally call S block, is known as the S orbital. So when you say S orbital, that S stands for the sharp orbital. Why the name sharp? Sharp in the sense that when you are moving from left to right on the periodic table, from left to right, the elements here are very reactive. They are metals. So we call them the first one. There are 2 members here. We have the 1A and then the 2A. The 1A, which is group 1, is known as alkali metals. Group 1A is known as alkali metals. Then group 2A is known as alkaline F meters. So you can see from this S, we don't want to say sharp. We want to continue saying sharp orbital, sharp orbital. So we prefer to use the name S orbital. So that's the sharp orbital. Now when we finish with the sharp orbital, this sharp orbital, you can see it has only two. It can only be occupied with two electrons. We have two members there. That is group 1A and 2A. So there are only two. So when you are filling the orbital, the S orbital, normally we can only fill that with maximum of 2 electrons. What it implies is that there are only two members, groups in the S orbital. That is the concept. Now, let's move on to the next block and discuss a few things there. When we move on to the next block, let's come to this block first, the P block. The P block is also known as the principal block. So P, we don't want to always keep saying principal block, principal block. So we prefer to use the word P block or P orbital. So this is the principal orbital. Now when it comes to the principal orbital is degenerate. When it says an orbital is degenerate, it means that that orbital has the same volume or energy level, but different orientations or different directions. So with this P orbital, it has three directions, which is Px, Py, and Pz. There are three divisions, Px, Py, Pz. Now when you want to draw this directions on the Cartesian plane, this is our x-axis and this is our y-axis. So we can have a direction like this. The P orbital is dumbbell in shape. So this is the shape of the Px. Now in most of our disciplines or textbooks, you can see Py like this, but we prefer to have it like this, P X, Y, Z. So most often you see the Y here like this. And then there's a Z. So these are the directions. Their energy levels are the same, but they have different directions or different orientations. So that is one thing we need to know. Px, Py, Pz. Now when it comes to the P block, it starts from group 13, 14, group 15, group 16, group 17, and group 18. They are members in the P block. Now when you count the number of elements there, you can see there are 1, 2, 3, 4, 5, 6. So the P block picks a maximum of 6 electrons. And they are divided into two divisions. One, first division, second division, and the third division. So that is basically about the P block or the P orbital. Now let's move on to this block, which is called the D block. Now the D block is also having the meaning diffuse, the diffuse block. So instead of saying D block, you can just say the diffuse block. Now with the diffuse block, it also has subdivisions. We will look at the main periodic table. It has been divided into 5 subdivisions. So this is the D block, D1 to D5. So with this D block, prefer to have it at the bottom. D2, D3, D4, D5. So this is the D block, the diffuse block. Now the diffuse block, it also has a maximum of 10 electrons. So it normally starts from this place, scandium, and ends at zinc. They are 10 in number. So you can see we throw these electrons singly before we pair them up in the opposite spin. So the d block can take a maximum of 10 electrons. That's the d orbital. So that is one thing we need to know about the d block. They are transition elements, and we'll talk about some of their characteristics. Now let's come back to the F block. The F block. The name F stands for fundamental. So instead of saying fundamental block, we prefer to use the word F block. So with the fundamental block, it has 7 subdivisions. One, two, three, four, five, six, 7. So with this F block or F orbital, it can take a maximum of 14 electrons. Feed them singly before we pair them up in the opposite spin, according to the Hand's rule of maximum multiplicity. So this is the F block. Now, when you read the periodic table and you are counting, at times you meet, or when you are counting, you normally get 15 instead of 14. The reason is there are some gaps. Some of the scientists left some gaps, so that when new elements are discovered, we can place them in those gaps. So when you count and you get some 15, there's no problem with that. But most of the periodic tables, when you count the F block, you get 14 elements there. Now in the F block alone have 2 subdivisions, or it is divided into 2 major divisions. So under this D block, which we call the transition element, the F block is also known as inner transition element. So this is the normal transition element. But this F block is also called inner transition element or inner transition metals. Now this inner transition metal is divided into 2. We have, normally for you to identify the divisions, we have an element which starts with La, which we call the lanthanide, and then Ac, which we call the actinides. So these subdivisions are also called the lanthanoids, or in some cases you see the word lanthanides. It's the same thing. Lanthanoids and the actinoids or actinides. For you to identify that, you use these 2 elements to identify that, the lanthanides and actinides. So when you flip your periodic table, you realize that the lanthanides start from atomic number 57 and ends with the 71. Those elements there are called the lanthanides. And then the actinium start from atomic number 89 and ends at atomic number 103. They are called lanthanides. So the lanthanides start from lanthanum and ends as lutetium. So that is the vast difference. It starts from 57 to 71. They are called the lanthanoids. And the actinium starts from 89 and ends as lawrencium. Lawrencium is 103. So those elements there, they are called the lanthanides and then the anthanides. So it means that the F block is divided into 2. The lanthanides and then the actinides. Now basically this is what we can say about the general scope of the periodic table. Now let's go into details. Now for us to get a detailed explanation of this is how the elements have been arranged. So basically, this is how the periodic table has been arranged nicely. They all have their boxes. Now, every box has an indication, so this is what you are going to do. There are so many questions that can be asked. So let's take any example of an element, any known element. So let's pick an element like sodium, which has atomic number 11. And in this case, we are supposed to write what we call the electron configuration for this sodium using the SPD notation. So there is a general rule for writing electronic configurations. So which we have done in my previous videos. If you have not watched, try to watch to get the concept there. So this sodium is written as 1s2, 2s2, 2p6, and then 3s1. Now, anytime we write electronic configuration, these orbitals I've already explained. The S stands for the S orbital, the P stands for the P orbital or the P block. Now, when you write electronic configuration and you get what you call the outermost electron, this outermost electron can predict a lot of things. Now, as soon as I write the electronic configuration, I'll be able to know the exact block that that particular element belongs to. And anytime I write an electronic configuration, the outermost block indicates that that element belongs to that block. So I can ask a question. Explain why sodium is an S block element. In your explanation, you are supposed to tell us that sodium is an S block element because the electronic configuration of sodium is written as, then you write your electronic configuration. Since the outermost electron, that is the force on the S block, that is 3s1, it implies that sodium belongs to an S block. So it implies that anytime you write configuration, your outermost electron will determine your block. So with this, we can get a lot of information. Look at this. It means that sodium belongs to S block. Your outermost electron, which is 1, also indicates that sodium belongs to group 1. And the 3, which is the principal quantum number, indicates that sodium belongs to period 3. So the principal quantum number determines your period number. The outermost electron determines your group number. And then the S block indicates your S orbital indicates your block. So from here, I can confidently say that sodium belongs to group 1, it's in the S block, and it's in period 3. So I can throw that on the periodic table. Let's do that quickly. So I'll come and check for all group 1 members. These are the group 1 members. I cannot place sodium here because sodium is not in period 1 because the principal quantum number for the sodium is 3s1. So it means that I can place sodium in this group confidently or comfortably. So anytime we write configurations, it will tell you the exact place to place that particular element. Let's also write for elements like, let's use lithium, atomic number 3, 1s2, 2s1. This implies that lithium belongs to group 1. It is in the S block, and these are S block members. These are S block members. These are D block members. These are P block members, and there are down values for the F block. So this indicates that lithium belongs to group 1, it's in the S orbital, and it is in period 2. Because the principal quantum number here indicates that it is in period 2. So with that, you can look for group 1 elements. This is my group 1. So the period is period 2. So it means lithium is here. You can place lithium here comfortably. Now, there are some exceptional cases. For instance, anytime you write the electronic configuration of an element and the outermost electron exceeds 2, when I say it exceeds 2, it means from 3 and above. Always add 10 electrons to get the group number of that particular element. It's very important. What it implies is that if you write the electronic configuration of any element and the outermost electron exceeds 2, that is 1 is above 2, so 3, 4, 5. Add 10 so that you get the actual group number of that element. The application simply means when you write for an element like aluminium, for instance, It is having atomic number 13. And the configuration will be 1s2, 2s2, 2p6, 3s. This you are written up to, so 3s2, then 3p1. Now the question here is, how many outermost electron has aluminium? In most cases, most students post your answer in the comment section. Pause the video and post your answer in the comment section. Yes, I get you right. Most students will say it is having 1, but it's not so. Aluminium is not having outermost electron as 1. The valence electron of aluminium is this, 2 plus 1. The reason being is, these principal quantum numbers are the same. This is 3s2, 3p. So since the principal quantum numbers are the same, if you want to find the valence electron, you use 2 plus 1, which is 3. So aluminium has 3 as its valence electron, but you cannot confidently say that aluminium belongs to 3. No. Just like the rule I have given to you, this implies that you add 10 to the valence electron to get aluminium's actual group number. So in this case, aluminium will belong to what? Group 13 on the periodic table. Why are we adding 10? We are adding 10 because there are some elements we call the D block. They have occupied the space here. Now, one thing we need to know is that elements on the S block and then the P block, we call those elements main group elements. Main group elements are elements on the S, the sharp block, and the principal block. Those two elements there, so the elements here and the elements here are called main group elements. And so, in between the main group elements, we have a D block. So, that is what we added. From scandium to zinc, we have 10 elements. So, you can see that manganese is here, then iron is here, then I think from iron we have nickel is here, cobalt, then we have copper. Okay, cobalt will come first, then nickel. So you can see from here that we have from here this is 21 to the 30th elements. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can see from there that it gives us what? 10. So whenever you write and it's above 2, you have to add 10 elements or 10 to the number to get a group number. So aluminium will not belong to group 3, but rather it will belong to group 13 on the periodic table. And the principal quantum number will determine your period number. So this aluminium belongs to period 3, but group 13. So this is group 13. These are group 13 members. This is period 2. So aluminium is supposed to be somewhere here. So this is basically the rule for writing the electronic configuration and arranging elements on the periodic table. Now from here, you can group any element you wish. And wherever the elements are positioned, it is the function. It is the property of the atomic number. So we have a law called the periodic law. The first law was propounded by Mendeleev. Mendeleev has a law which is called the Mendeleev periodic law. And then the modern periodic law propounded by Henry Moseley. We call that the modern periodic table or modern periodic law. Now what the periodic law is saying that the position of this element, all the scientists try to group these elements based on their atomic masses. So they said the position or the function of these elements is the periodicity or the periodic function of their atomic masses. But there was a scientist which we call the modern periodic chemist. He said that the arrangement of these elements, it is the function or the periodic function of their atomic numbers. So, if you want to really study this, it is the atomic number that is giving them the positions. So, we can now group all the elements in this order. So, let's look at some few things. Hydrogen is here, helium. So lithium, beryllium is here, boron, carbon, nitrogen, oxygen, fluorine is here, neon is here. Sodium is here, so magnesium will be the next one here. Aluminum is already here. Silicon, phosphorus, sulfur, chlorine is here, argon is here. So from argon, we have potassium, calcium. Now, when we are able to write this, there are some of the elements you know where they are positioned. For instance, when you pick the group 1 elements, you know that under this potassium, we have rubidium. Under this rubidium, we have cesium. And under cesium, we have francium. You also know that under this calcium, we have scrotium. Under this scrotium, we have barium. Under this barium, we have radium. So you should be familiar with these ones. And when it comes to these group members, the groups that are very important, we need to discuss them, talk about them. These are the 18 elements. Under this argon, we have krypton. Under krypton, we have xenon. Under this xenon, we have radon. Under this radon, we have rhodium. Then when you come here, under this chlorine, we have bromine. Under this bromine, we have iodine. Under this iodine, we have astatine. Then we have this. So these are the main group elements. We are going to discuss some few things about them. Then we end the video here. Now, when we pick these group 1 elements, we call these group 1 elements alkali metals. These alkali metals are reactive. They have their outermost electron to be NS1. What it means is that if you write the configuration of all these, they are all having one outermost electron. For instance, if I want to write the electronic configuration for hydrogen, I will have one S2. So now, I'm not interested in writing the whole configuration, but I'm interested in writing the valence electron. So the lithium will now have 2s. Okay, this is 1s1, this hydrogen. So lithium will be 2s1, this one will be 3s1. I'm just writing the outermost electrons. This will be 4s1, this will be 5s1, 6x1, and then 7x1. So this is how we write the configuration. You can check from here that in a section of this hydrogen is not part of the transition metals. This hydrogen is not part of the alkali metals. Because hydrogen actually, when you look at the characteristics of these metals, hydrogen does not have any of them. Hydrogen can behave like this, as H plus, and at times it behaves like this. When it behaves as H minus, we call that hydride. So hydrogen is not part of the transition metals on the group 1. When you are asked to give examples of alkali metals, hydrogen is not part. So we have lithium, sodium, potassium, rubidium, cesium, francium. These are the transition metals. Now when it comes to group 2, they are also having similar number outermost electrons, which we call them the alkali earth metals. They also have, so we are having 2s2, 3s2, 4s2, 5s2, 6s2, and then 7s2 in this order. So you can see that they all have an outermost electron of ns2, meaning they all have 2 electrons at the outermost shell. Now, these 2, they have a peculiar property which we'll talk about in our next video. We are going to look at some of the trends that happens when we are moving down the group. That is when we are moving from top to bottom of the periodic table. There are so many periodic trends that we are going to look at for. We'll be looking out for ionization energy or ionization potential or ionization enthalpy, the same thing. Either say ionization enthalpy, ionization potential, or ionization energy, the same thing. We'll talk about that. We'll also talk about some properties like atomic radius or atomic size and other things. But there are other names for this group. I'm giving this as an assignment and I want to see your answer in the comment section. What name is given to all group 15 elements? They have a special name. Post your answer in the comment section and let's discuss about that. And what name is given to group 16? They have a special name. Post your answer in the comment section. Now when it comes to group 17, they have a name called halogens. Group 17. They are called halogens. And then group 18 members are called noble gases or inert gases or rare gases. So I would like to end this lesson here. Thank you for watching this video. I would like you to subscribe to the channel, like the video, comment if you don't understand anything, you can ask in the comment section, and share the video to your friends. Thank you, and see you in my next presentation on periodic trends. Bye bye.